So remember when we did continuously compounding, we used the natural number e, which was 2.71 and 828. It keeps going on continually. It's an irrational number like pi. And we've used it as the base of an exponent, right? So e to a power, we have done that. So that function is y equals e to the x, which we have used. We used it with, like I said, continuously compounding. It has an inverse. Just like anything else, y e to the x can be written as a log function. Log, my base is my e. My exponent is what I'm solving for. And log of what? That would be the y. And so you have log base e. But what you'll notice is the notation for log base e is just ln. And in your calculators, you have a log, that is base 10. And you have an ln, and that is base e, all right? So you have a base 10 and you have a base e. And by the way, change of base formula works for either base 10 or base e. So if you were to say in your calculator, log base 3 of 10, you can in your calculator say common log of 10 divided by common log of 3, or you can say natural log of 10 divided by natural log of 3. They will give you the same answer because change of base works from any base to any other base. So in your calculator, you actually have two bases. You have a base 10 and a base e automatically programmed in there. All right. And so when you're writing base e, you don't need to write log. You need to write ln. And that is an assumption that it's log base e. Just like log without a base is an assumption that it is base 10, common log. This one's called the natural log. All right, everything works the same. So all of your condensing, your expanding, your solving of equations, they all work the same for natural logs as they do for any other log. First one, it says write 3 ln of 6 equals ln of 8 as a single natural logarithm. And so we are going to use our condensing rules. 3, that's going to go up as an exponent. So I have ln of 6 cubed minus ln of 8. The subtraction, that's going to allow me to do it with division here, right? And then this is evenly divisible. So if I take 6 and I cube it and I divide it by 8, I am going to get to 27. So 1 natural log. And so all of your condensing rules work the same. Go ahead and quickly try those 3. For the last one, yes, these become the exponents for both of them. So I have ln of 3 to the 1/4. And we're going to multiply that by x to the 1/4. They are both to the 1/4 power. So that is ln of 3x to the 1/4. And remember, any fractional exponent is just a root. So that's the root, the 4th root of 3x. A spacecraft can attain a stable orbit 300 kilometers above Earth if it reaches a velocity of 7.7 kilometers per second. The formula for the rocket's maximum velocity, v, in kilometers, is, and they give us this formula right here, v equals negative 0.0098 t plus c ln of r. So this is the velocity calculation. Then they explain what each thing is. The booster rocket fires for t seconds. That's my time. The velocity of the exhaust is c kilometers per second. The ratio of the mass of the rocket with fuel to its mass without fuel, why did he jump, is r. And so they give me that. Suppose a rocket, and so now they have explained everything within the formula, all right? Suppose a rocket used to propel a spacecraft has a mass ratio of 25. Mass ratio of 25. They just gave me r. An exhaust velocity of 2.8. exhaust velocity, they just gave me c. All right? And then it says a firing time of 100 seconds. They just gave me t. Okay? So all I'm going to do is I'm going to plug in that information. All right? So I'm going to take the formula. V equals negative 0.0098 t plus c natural log of r. Can the spacecraft attain a stable orbit 300 kilometers above the Earth? What was the stipulation? There was an if-then statement. It can obtain a stable orbit if. What is the if in the very first sentence here?
7.7 kilometers per second.
If the velocity is 7.7 kilometers per second. We need to calculate this velocity and see if it is 7.7 or more, which means it will be a stable 300 kilometers above the Earth. All right? So we're just going to plug in the information. We're going to say negative 0.0098. What is my time for this one? 100. Plus C. What is my mass ratio here? 25. Natural law. Oh, wait. I did that backwards. Sorry. Yes, 2.8. Exhaust velocity. And then my ratio is 25. All right. So in order to solve for my velocity, I'm literally just going to plug, all of those are numbers. Negative 0.0098 times 100 plus 2.8 natural log of 25. Literally just plug it in and solve for what your velocity is. So make sure you can put it in your calculator and calculate it. So when you do all of that, you should get, when you round it, 8.0 kilometers per second. So the answer is yes. This is greater than 7.7, so it can obtain a stable orbit 300 kilometers above the Earth. All right, when you plug everything in, you should have gotten 5.4, and no, this would not be stable. Now,
5.3, so you want to round?
yeah, so round, I'll tell you how to round. I want to look at critical thinking together. Suppose a rocket, so the one you just calculated, as designed, cannot provide enough velocity to achieve a stable orbit. Look at the variables in the velocity formula. What alterations could be made to the rocket so that a stable orbit could be achieved? So when you put this in, you put in negative 0.0098. Your time should have been 30 seconds, right? Plus your exhaust velocity was 2.1. And then your mass ratio was 15. All right. What could you change here?
A longer firing time.
A longer firing time would make it higher. What? So your firing time is right here. That would actually increase your negative, would it not? A longer firing time, would that not increase your negative? Your firing time is being multiplied by negative, correct? What did you say, Ethan? Yeah, your exhaust, right? Is that what you're talking about? Your exhaust velocity. How quickly that exhaust goes out would actually bump up your positive, right? Would bump up your positive. Something else. What's the other thing that would bump up your positive? Your mass ratio. Your mass ratio. So in this case, we have natural log of 3x plus 5 squared equals 4. And so I am solving for something that is within the natural log. And so I really need to get rid of this natural log. Now, before I do, you may want to expand here. So expand and get just the natural log by itself, and then see if you can get rid of the natural log. So what can I do with expansion here?
Use E. Take the 2.
Yeah, we will use E. So first we're going to take this 2, and we can pull it out in front. So we have 2 natural log of 3x plus 5, and that equals 4. And so I am going to divide by 2, and I have natural log of 3x plus 5 equals 2. And now I'm going to use my e. So this is ln is a base e, so I'm going to do a base e on both sides. And so on the left-hand side, my e and my ln cancel, and I just have the 3x plus 5. And on the right-hand side, I have e squared. Remember, e is a number, so I have a number on the right-hand side. I am solving for x, so what do I need to do to continue to solve for x here? Subtract the 5. All right, so I have 3x equals e squared minus 5, and then my last step here, divide by 3. And so x equals, and you can put this into your calculator, you will need a parentheses here, e squared minus 5, close parentheses, divided by 3. But when you do that, you should get rounded to the nearest thousandths place. 0.796. All right, use natural logs to solve. When you have something like this, your goal is to get the e by itself and then to use natural log to cancel out the e. So for this one, I would subtract the 2.5 first. 7e to the 2x equals 17.5. Divide by that 7. So e to the 2x equals 17.5 divided by 7. All right, so I'm going to pull it over here. E to the 2x equals 2.5. And now I'm ready to take my natural log of both sides. Natural log will cancel out an e base, all right? So I can say natural log here, natural log here. And on the left-hand side, those cancel. I have 2x equals natural log of 2.5. And so my final step here is to divide by 2. So x equals the natural log of 2.5 divided by 2, which is 0.458. All right, so get your e by itself and then take the natural log. If you're doing a log, get your log by itself and then use your base. This is true of all logs and all bases. Get it by itself, take a log to cancel out a base, take a base to cancel out a log. So go ahead and try those two. So before, you just had to know P e to the RT, and you would plug in your P, you'd plug in your R, you'd plug in your T, and you would solve for what your account had in it. In this case, we're doing something different. An initial investment of 100 is now valued at 149.18. The interest rate is 8% compounded continuously. How long has the money been invested? They are now asking you to solve for time, which is something that is in the exponent position. So we would still use our P e to the RT. All right, but we're going to plug in the things that we know. We know what it's worth now. That is our A, 149.18. We know our initial investment of $100. E to the R, we know our interest rate is 8%, so I'm going to put 0.08. I do not know my time. So now I'm solving for something in the variable. I'm going to get the E by itself, right? And I have E to the 0.08 times T equals 149.18 over 100. Now I can take the natural log of both sides. These cancel, so I have 0.08 times T equals the natural log of 149.18 over 100. And then I can divide both of those by 0.08. So time is going to equal the natural log of 149.18 over 100 divided by 0.08. They round to the nearest number of years, so 5 years is how long it has been invested. So we're taking the same formula, but now instead of solving for what the account has in it, we are solving for something that is in the variable position. You could do the same thing with the interest rate as well. If they told you how many years it had been invested and wanted the interest rate. So go ahead and try number 5. Check understanding.